Hello and welcome to Raw2 Talks. Today with the second part on second order theory and geometric nonlinearity. Last time we have seen a simple Euler beam with a compressive load, and we have shown that the second order theory explains the situation in the deformed state. So we have deformed the beam to this position and could show that it's exactly the same as the result of the second order theory. Now let's have a look at some more practical piping system. So in this example I've put a horizontal beam on two supports on each side. I've used different discretizations here to see the impact of the discretization, and I've chosen a diameter of 400 DN 400 and a distance of around 20 meters here. This corresponds well to the allowable distance for weight loads for DN 400. So let's run the calculation again with linear calculation, first order theory, second order theory, and geometric nonlinearities. So the first example is linear elastic, and we can first of all see that the deflection here of in the middle of the beam, which is just supported on both sides, is 38 millimeters, and it is exactly the same for all three discretizations. So the discretization is not important to get correct Raw2 results for linear first order calculation. Now we can also see that there is no axial force and that the pipe holds just by the bending moment here. If I use a second order theory, it is exactly the same situation because there is no compressive load here yet. But if I consider second order theory with geometric nonlinearity, the fact that the pipe will bend down and also the fact that both ends are held in the axial direction will create additional axial forces, which are now 20 kilonewtons. And these 20 kilonewtons will result in second order theory to give reaction forces upwards, and these will reduce the deflection from 38 to 37.7 millimeters. So there is a tiny little change in deflection due to the second order. Now this is so small because the piping section is so big. How about if the piping section gets any thinner? So let's modify the system and go to a smaller DN, and I will go all the way down to a DN 80 here. So I will run the calculation, and we see we get a warning: check numerical stability for the load case second order nonlinear geometry. Let's have a look at the results. First of all, deflection of first order theory. We can see that the deflection is 800 millimeters now. Still no axial force, and the 800 millimeters is the equilibrium with the bending moment here, which is quite high for the small DN pipe. But if we go to second order nonlinear, we can see that now instead of a huge bending moment, we get a huge axial force because the bending down shortens the pipe with a second order effect. This gives a return bending moment, and this reduces the deflection to 134. And now we can understand the warning from Raw2. Actually, if you look at the stability from the bending stiffness, it's only preventing the deflection, so it gets 800 millimeters, and now we add some geometric stiffness on top of it, and this stiffness increases the stiffness so much that it goes all the way down to 134. So a lot of the stiffness actually comes from the second order effect. Now, is this a good idea to avoid putting supports in a pipe? If we have a look at the equivalent stresses here, they are around 75 Newton millimeter squared. This could be acceptable, but well, let's have a closer look what happens if we now add a load case with some temperature in it. So we quickly create another load case just in the same way, but now we call it hot, and we'll take over all the data from this last load case, do second order theory, geometric nonlinearity, and we apply a temperature now from let's make it just 60 degrees, yeah, so a little bit hotter. And now let's run the calculation to see what happens in the hot case. Well, actually we won't see what happens in the hot case because the calculation does not terminate. System is buckling, yeah, and so this is not a good idea. So we can sum up that if you're using a pipe system configuration which is let's say reasonable with a support distance that is acceptable, then the pipe will be able to hold itself by the bending moments, and the secondary order effects are really negligible. It's only required for situations where you try to use the axial force to hold the pipe, and this is actually not a reasonable situation for most piping elements because they can get hot. Okay, I would like to show you one more model, and this model you've probably seen it if you have ever participated in a RAW2 training, because it's one of our basic model to start our training with. This ordinary piping system, 3 ends, some supports, and I just want to see what is the difference on such a system between linear first order theory and second order theory. So I will go directly to the load case definition and take, for example, the operating case here, create a new one, call this operation second order, and basically use exactly the same loads but calculate it based on second order theory. And now when I run the calculation and check the results for this new load case, we can actually see no difference in a qualitative way between the operating case and the operating non-linear case. So let's try to quantify it a bit more. So I will go to the superposition tab. I will switch on the manual superposition, and now I create the difference between those load cases. So this is a second order, and I will take the operating case and times a factor of 1 and the second order operating case, but in this case I will just subtract it by multiplying it by -1, and the resulting load case, we are going to use it in the support load superposition, and we're going to show this graphically so we can basically show the results. So let's calculate the support loads and see what is the difference between those two calculations. And the difference would now show up here as superposition results. And well, if we look at the scaling here, I have to multiply it by 6,000 to see the difference. So actually the displacement is in the 10 micrometer range, so it's really negligible. Yeah, so for an ordinary piping system, the second order theory is not required. Finally, I would like to show a system where second order theory is useful. So this is a chimney, and the chimney goes up around 60 meters, and then we have some ropes to hold it in place against wind loads. So I've applied some wind loads here on the chimney itself, but also on the ropes. And then I've again calculated first order, second order theory, and second order non-linear geometry. So let's have a look at the results in this case. Well, the first order theory, because the piping, the ropes here are so soft, they have almost no bending stiffness, the deflection for the ropes is completely wrong in the non-linear calculation, or wrong, let's say it's not representative. Whereas the piping system itself still looks pretty okay. We have around 28 millimeter deflection here at the attachment point and 37 on the top, and in the middle here in between the supports 53 millimeters. So if I want to show this a little bit more in detail, I can maybe just zoom in on this part and show only this selected segments, switch on displacement, and now we can see the deflection here of the main beam, main piping system itself, due to the wind load. If I go to the second order theory, and I go directly to second order non-linear theory here, you can see that now the deflection increases. So we're actually having the compressive loads due to the ropes, and this will create an additional deflection in the main chimney. And if we show all the segments now again, we can see that the deflection in the ropes itself now becomes reasonable, because now we have the second order effect, which actually creates a whole lot of additional stiffness due to the high pretension loads. How did the pretension loads end up? I actually added here some pretension as a load, and it's 20 millimeters of shortening to get the initial pre-stress in those ropes. Without those pre-stressing, the system would not be stable and I would not get a numerical results. By the way, it's if you look at the difference between this first order and the second order deflection, this is a situation where it's situation where it's very difficult to obtain convergence in row 2, because there is so little initial stiffness due to bending, and practically the total stiffness comes from second order effect. So this is not necessarily the way I would analyze this situation. I will probably replace these ropes here just by equivalent springs, and I would still get a reasonable results here, yeah? And I would not try to figure out the exact bending curve here in the ropes in this case, but I'm interested in the piping system itself. But okay, for this example it is important to have the second order effects, otherwise the vertical compressive loads on this chimney would not be taken into account correctly. And maybe finally, for the buckling shapes, if I look at the buckling shape, so the factor of loads would be 2.2 until buckling, so this would be a little bit too close. Usually you try to remain a safety factor of 3 against elastic buckling. Yeah? Okay, this concludes my talk for today, and let's see you next time.